Welcome back to the Deep Dive. Today we are taking on a paper that honestly feels like a major course correction in how we think about vision and language AI.
It really does. For years, the default has been these huge, and I mean huge, generative models if you wanted a system to see something and talk about it.
Right. And today, our mission is to unpack a genuine alternative, VL-JEPA. That stands for Vision Language Joint Embedding Predictive Architecture.
A bit of a mouthful, but the idea is powerful.
We want to understand why it's being called the first non-generative model that can handle these general vision language tasks in, and this is the key, real time.
And how it gets better performance with way more efficiency than the traditional models.
So to really get this, we first have to talk about the current VLM bottleneck. Why are the existing models, a problem?
Well, think about where you need the stuff. Wearable tech, robotics, live video analysis, latency is everything. You need an instant response.
And the common models, like an InstructVLIP or QuenVL, they don't do that. They build their answers token by token, word by word.
Exactly. It's an autoregressive process. It's inherently slow and sequential, and that creates two massive problems.
Okay, what's the first one?
The training cost is just astronomical. Because the model isn't just learning the meaning of what it sees, it has to learn every possible way to say it.
So all the different paraphrases, the grammar, the style.
All of it. It's modeling a ton of task-irrelevant linguistic noise. It's just wasted computation.
And the second problem is that real-world lag. You have to wait for the whole sentence to spit out before you know what it's trying to say.
Which is a non-starter for streaming video. It's just too slow. And that's the bottleneck VL-JEPA is designed to completely smash.
All right, let's unpack that core conceptual shift then, because this is where the magic happens. What is the fundamental difference in what VL-JEPA is trying to predict?
It all comes down to the space where the prediction happens. A classical VLM tries to predict the actual text, the response Y, in what we call the data space, token by token.
So if the right answer is the sphere is moving, but it predicts the ball is rolling, it gets penalized.
Heavily penalized. Even though the semantic meaning is basically identical, it's trying to do this perfect, high-fidelity reconstruction of language.
Which, as you said, is computationally wasteful. So how does VL-JEPA flip that?
It doesn't predict the text at all. It predicts a continuous embedding, let's call it SY, which represents the meaning of the text. This happens in an abstract, continuous, latent space.
So it's not predicting words, it's predicting a point in meaning space.
Exactly. The training goal becomes so much simpler. Just get your predicted meaning close to the target meaning. Forget about the exact words.
And that move to an abstract space has a huge benefit, right?
Right.
Why does that simplify learning so much?
It forces the model to focus only on what matters, the task-relevant semantics. This is a game changer for what are called ill-posed tasks.
Ill-posed tasks. Give us an example.
Okay, imagine you show the model a video of a kettle boiling and whistling like crazy, and you ask, what's happening?
I could say, the water is boiling or the kettle is whistling. Both are correct.
Right, and 100 other variations. To a classic VLM, those are two totally different orthogonal targets in the token space. It's trying to learn two separate things.
That sounds incredibly inefficient.
It is, but the Y encoder in VL-JEPA takes both of those correct answers and maps them to very nearby points in the continuous embedding space. They become one single coherent semantic target.
So it filters out all the linguistic static and just hones in on the core concept.
That's it, exactly. It solves the ambiguity of language by focusing on the semantic destination, not the dozen verbal paths to get there.
Okay, so that's the theory. Let's look under the hood. How is this thing actually built? It's got four main parts.
It does. First up is the X encoder. This takes the visual input, the video or image, and maps it into a visual embedding.
And they didn't build this from scratch.
No, and that's a key point. They took a frozen, pre-trained V-JEPA2 model, a really powerful vision transformer.
Why freeze that specific one? What's the advantage?
V-JEPA models are known for producing really robust semantic visual representations. By freezing it, they're basically saying, we already have a great visual understanding of the world. They just need to focus their training budget on aligning that vision with language.
Smart. So that handles the vision side. What about the text? The second component is the Y encoder.
Right. That maps the target text, the answer, into its meaning embedding, SY. And again, they initialize it from a strong foundation, embedding JEMA in this case.
And then we get to the heart of it, the predictor.
Yes, this is the most critical piece. This is what does the learning. It takes the visual embedding and a text query, like a question, and then it predicts the embedding of the answer.
And this part is a transformer, too.
It is. It's built from the last 8 layers of a Llama 3.2 model, so about 490 million trainable parameters.
The last 8 layers. That's specific. Why?
Because the final layers of a big language model are thought to hold the most abstract, high-level semantic knowledge. So they're basically inheriting a sophisticated understanding of semantics and causality without needing the entire huge generative model.
That's incredibly clever recycling.
Ah.
Okay, and the last piece is the Y-decoder.
And crucially, the Y-decoder is only used at inference time when you actually need to see a human-readable sentence. It is completely left out of the main training loop.
And that's where the big training efficiency boost comes from. You're not spending cycles training a massive language generator.
Exactly. You're just training the much smaller predictor to get the meanings right.
The paper mentions using bidirectional influency loss. That sounds technical, but why is that important? Why not just, minimize the distance between the prediction and the target?
You could, but that can lead to something called representation collapse.
Representation collapse.
It's the model finding a lazy shortcut. It just maps every single input, no matter what it is, to roughly the same point in the embedding space.
So the distance is always 0. The model thinks it's doing a perfect job, but it has learned nothing.
Precisely. InfoNC loss prevents that. It enforces 2 things. Alignment, meaning the prediction and target should be close, and uniformity, meaning embeddings from different inputs should be pushed far apart. It forces the space to stay structured and meaningful.
Got it. Okay, let's move to the proof. The controlled experiments. They put VL-JEPA head-to-head with the standard generative VLM. What did they find?
They confirm the whole theory. The VL-JEPA predictor has about half the trainable parameters of the VLM baseline's decoder. Half.
And the performance.
Even with fewer parameters, it showed consistently higher performance at the same training steps. The learning curve was just much, much steeper. It's clear proof that predicting in the embedding space is just more sample efficient.
Which brings us to the real-world goal, inference speed. This is where it matters for, say, a developer building a real-time application.
Absolutely. The non-autoregressive design is the key. It produces that semantic embedding in one single forward pass. No waiting.
And this enables something they call selective decoding. Can you break that down for us?
Yeah, the analogy they use is great. Think of a professional transcriber at a long, boring meeting.
Okay.
They aren't constantly typing every single and. They're listening, monitoring the meaning of the conversation, and they only start producing text when something new or important is said.
They wait for a semantic shift.
Exactly. VL-JEPA does the same with a video stream. It constantly outputs its stream of semantic embeddings. You can average them over a small window to stabilize it, and then you only fire up the expensive text decoder when you detect a big change in the embeddings.
So when the variance in that window spikes, you know something new has happened.
Yeah.
And that's the moment to generate a text description.
You've got it. The system is always tracking meaning, but it only spends compute on generating language when it's absolutely necessary.
And the numbers on that are pretty wild.
They are. This strategy cut down the number of decoding operations by about 2.85 times, with basically no loss in the overall quality of the output. For a commercial streaming application, that is a massive, massive saving.
And beyond the speed, it's also a unified generalist model. It's handling all these different tasks, VQA, classification, retrieval, with one architecture. How does it do that?
It's all about distance in that embedding space. For VQA, or classification, where you have a set of possible answers, you just encode all the candidate answers into their embeddings.
And then see which one is closest to the model's prediction.
Right. It becomes a simple nearest neighbor search, a matching game.
And for retrieval, finding a specific video clip with a text query?
Same idea. You encode your text query into an embedding, you map all your candidate videos to their embeddings, and then you just rank them by similarity. It's elegant.
So how did it actually do on the benchmarks against bigger, more established models?
It did really well. The base model, before even fine-tuning, beat larger baselines on a range of zero-shot classification and retrieval tasks. And it was especially strong on benchmarks that involve a lot of motion and action.
And then for VQA, after fine-tuning?
It was right up there, performing on par with big names like InstructBLAP and QuenVL on really tough data sets for things like reasoning and counting.
Okay, but the result that really made my jaw drop was for the world prediction benchmark. Can you explain that task again?
Right, this one is fascinating. It's an inverse dynamics task. They show the model two states, state A, a closed door, state B, an open door, and the model has to identify the action that caused that change.
So it has to infer the cause from the effect. It's testing causal reasoning.
Deep causal reasoning, and the performance.
This is the crazy part.
VL-JEPA SFT achieved a new state-of-the-art, 65.7% accuracy. And it didn't just beat other VLMs, it surpassed frontier LLMs. We're talking GPT-4o, Claude 3.5 Sonnet, Gemini 2.0.
Wait, so this much smaller, non-generative, embedding-based model is better at causal reasoning than the biggest models on the planet.
For this specific visual task, yes. It strongly suggests that by focusing only on predicting coherent semantics, it builds a cleaner, more robust internal world model. It's not distracted by having to also be a perfect poet.
So let's tie this all together. What does this mean for the future? We have a more efficient, non-autoregressive architecture that's great for real-time applications and surprisingly powerful at world modeling.
The main takeaway is that we finally have a model that blends the best of both worlds. You get the unified architecture of a CLIP-style model with the conditional prediction power that was usually reserved for these giant VLMs.
And it does this while being more sample efficient to train and way more scalable to deploy, especially with that selective decoding.
It's a huge step forward for any application that needs fast, dynamic intelligence.
But the paper is careful to say this isn't a VLM killer. Not yet. So what are generative models still better at?
And that really is the million-dollar question for the field. Generative models excel at tasks that require complex, chained, sequential reasoning. Think multi-step planning or tool use, where the model has to think out loud, token by token.
It's hard to do that kind of step-by-step reasoning in a single continuous embedding.
Exactly. So the next frontier isn't just about prediction, it's about how you build on this VL-JEPA foundation to enable that kind of complex, iterative reasoning, but purely in the latent space.
They've solved the efficiency and prediction problem. Now they need to scale the reasoning.
Precisely. The challenge is building an architecture that can manipulate these predicted embeddings over time to achieve agentic behavior without ever needing to fall back on generating text as an intermediate step.
A truly fascinating path forward. Thank you for walking us through this.
My pleasure. It was a great paper to break down.
And thank you for joining us. We'll catch you next time on The Deep Dive.